maybe I'll give you just this recap. So what did we get last time? If you know the graph of y equals f of x, then how do you get the graph of f of x plus c? Perfect. And maybe if you want something that seems like more technical sounding, add c to all y values on the graph. All right, what if you do the addition inside of the parentheses, f of x plus c? And you'll notice I'm like skipping the subtraction. If addition means go left, then subtraction means you go left by a negative amount. That should be okay. That translates to subtracting c from not y values, but x values. Y equals negative f of x. Yeah. Good. Reflect over the x-axis. And if you like, that's the reasonable thing, because what does that do? That multiplies all y values by negative 1. All right? What if I have the negative sign inside of the parentheses? F of negative x. Cool. And you know what? I'm going to underline this in yellow because I'm going to change it to something equivalent once I get down to these 2 bullet points. Right. There are 2 things left on the list. What if instead of multiplying by negative 1, what if you multiplied by an arbitrary constant? But maybe it's worth leading into this by just doing 1, maybe 2 examples. And I'll see what people's preferences. So on page 43 of them notes, let's sketch this graph, and I'll see how we all feel. Should I go through the example, or would you like to go through it, and then we come together? Should I keep talking? Cool, then I will. Those of you who would prefer to do it on your own, go for it. If you even want to, like, in reasonably hushed tones, collaborate with each other, go for it. So, there's the thing that I would like to graph. So it looks like there are 3 things that I need to do. I need to deal with this minus sign. I need to deal with that minus 3. I need to deal with that plus 1. The ordering of things matters. Which one should we do first?
The minus in front of the equation?
That seems reasonable. Yeah. I guess before we should even do that, let's start with like the obvious choice of elementary function. I know what the graph of y equals absolute x looks like. So the first thing to deal with will be the negative sign, so negative absolute x. How do you get that graph? Yeah. You do the reflection that makes the y values negative. And so you said it right, but it's really easy to accidentally say that wrong. All right, what should we do next?
At this point, does it matter which t you do?
Let's try to intuit. So it looks like I want to go right 3 and up 1. Is going right 3 and up 1 the same as going up 1 and then right 3? It is. If you like, that's because Cartesian geometry is based on a Euclidean geometry system. If you were doing all of this in some other hyperbolic setting, then it would make a difference. Like on the surface of the Earth, it's hard. If you walk 100 miles east and then 100 miles north, that'll get you to a different point than 100 miles north, then 100 miles east. And maybe the most convincing place to try to do that is if you're really close to the North Pole. Okay, but that's not what I'm talking about right now. We're talking about planar geometry. So let's do both at the same time. So how should I shift to account for the +3, -3, and +1?
Move to the right 3 and up 1.
Let's move to the right by 3 and up by 1. And so, right 3, up 1. So where will that point at 0, 0 wind up?
3.
3, 1? That seems sensible. 1, 2, 3, up 1. And it'll have negative slope to the left, so I guess I better go down at a slope of 1. Nope, that's positive slope. Cool. That seemed pretty okay. How do people think so let's deal with the order. How important do you think it was that we dealt with that negative sign first?
What?
Yeah, it turns out to be, yeah. Yeah. Should we do people think they would benefit by doing a quick experiment to see what happens if you did these moves in the wrong order? Yeah, why not? For some value of the 1 important. Let's see what happens. So let's do the same thing. Let's graph negative absolute x minus 3 plus 1, and let's intentionally do things in the wrong order and see how it turns out. So, oh yeah.
Thank you.
So, let's start at the same place. There's y equals absolute x. Let's deal with these things first. Let's go right 3, up 1. 1, 2, 3, up 1. And this is now the graph of absolute x minus 3 plus 1. All right, let's do the reflection. So, when I do the reflection, there's this corner point at 3, 1. Where will it go when I do the reflection that I need to do in the next step?
3 negative.
3, negative 1. Oh, cool, that doesn't look like the same graph as we got before, does it? And in fact, we can see exactly what this did. So this results in multiplying the whole function by negative 1, negative absolute x minus 3 plus 1. Oh, cool, so we just have an extra negative sign in front of the 1. We could fix this by just shifting an extra up by 1. So even if you do screw up the order of things, as long as you track exactly what function you're graphing at each step, you can correct for it at the end. Cool. Those ideas seem pretty okay? Nice. So, starting on the next page, let's aim to fill in these last 2 bullet points. What happens when you multiply a function by a number and multiply the input of a function by a number? And let's start with the one that feels most intuitive. What do you think should happen if you multiply a function by some number, like 2? How does the graph of 2 times f of x compare with f of x? Anyone have any intuition?
Vertical stretch.
There should be some sort of vertical stretch. And I guess that makes sense, if that C is 2, you're doubling all the output values. Output values are like Y values. So yeah, that seems sensible, all the Y values will get doubled. And let's just see this in practice. Let's pull up a quick interactive and see if that intuition is right. Give me a function you'd like to walk with.
3x plus 5.
3x plus 5. All right. Let's declare this constant. I'm going to let it vary. C times f of x. Now let's see. Does that green line look like it's the same as the red line but vertically stretched? Like the y values were all doubled? And now let's see what happens if we just let that parameter c change. As the constant c grows, the amount of stretch grows. When c is negative, it's a stretch in the negative direction. Cool. So, I think we have a pretty good idea what goes all the way down here. If you want to multiply, let c be a positive constant. If you know that the graph of y equals f of x, then you can get the graph of y equals c times f of x by multiplying all y values by c. And in fact, here's yet one more computer-generated graph to demo. There's a graph of y equals f of x. For f of x, this particular combination of absolute values. There's the graph of 2 times f of x. Does that look like just all the y values have gotten doubled? Yeah. The x-intercepts had y equals 0, so they stayed the same. 0 times 2 is still 0. This point 1, 1 became a point 1, 2. Let's see what happens when we do the opposite. So here's the graph of still the same function. F of x equals 1 minus absolute x minus 1. In fact, let's go to Desmos to do this. Stick with positive numbers. So there's the graph of this function. And let's start with c equals 2. And I now want f of c times x. So take a look at the red graph and then the green graph. What does it look like maybe relates them? How would you go from red to green?
I kind of moved the x-intercept to the left.
Cool. So the x-intercept has moved over to the left.
Then also changed the y value to, you divided the y value in half, you divided the x value in half, so you've got the, that's just what it looks like.
Yeah. So let's even track. Let's look at that corner point. I think the corner points are interesting. So there's the old corner point and the new corner point. How do they compare?
The x values got cut in half.
The x values got cut in half. And let's see if that checks out also with the x-intercept. There's one at 2, 0, and then it became one at 1, 0. X value also get divided by half? Or divided by 2, multiplied by a half? And I guess this one was already at x equals 0, so 0 divided by 2 is still 0. Oh, neat. Is there, let's see if this pattern holds up. Give me another constant that you might try this with.
7.
7. Cool. Let's take a look. So just visually, does that look like the x values have been 7thed? And I guess we can be precise now. Let's actually check the points. There's 1, 1. I guess 0.143, is that about a seventh? Hope so. We had this point at 2, 0. Yeah, well, if 1.43 is 1/7, then that's 2/7. So it looks like when you multiply the x values when you multiply the x in the function by 7, you divide the x values in the graph by 7. So in general, if you want to get the graph of y equals f of c times x, you don't multiply the x values by that constant, you divide. Dividing all x values by this constant. And I guess that fits into the pattern where, like, adding inside the parentheses became subtraction, multiplying inside of the parentheses became division. So just, whenever you do something inside the parentheses, you do exactly the opposite of what you expect. Cool. What do you think? Should we do some examples? Let's use this for some things. And I'll establish an order to do these in. So the first thing to do is deal with whatever is multiplied by the whole function. If you multiply the whole function by like 3, then deal with that first. Next, well, as we've noticed, it doesn't matter if you go up and left or left and up. Those are the same, so you may as well do those two moves at the same time. So whatever addition you do that next. And then last, deal with whatever is multiplied by the x in the function. And in fact, all that really matters is you do the plus d after the plus a, and you do the plus c before the multiplied by b. That's all that really matters. But this order does that. Gesundheit. So, let's use this. Let's go ahead, Gesundheit, and sketch the graph of negative 1/2 x minus 2, then you square it, then you add 30. And it says here to track where a few interesting points go, and we'll decide what points seem interesting as we go. So what elementary function should we start with? The squaring function? All right, that's like the interesting thing that this function does. So let's start with y equals x squared. And track some interesting points. So, what points count as interesting?
The origin.
Yeah, the origin counts as interesting. Intercepts are generally worth tracking. And that's also like a weird point. It's a taunting point. We'll have a special name for that point on parabolas maybe later. Well, maybe next time, called the vortex. Any other points you'd like to track on this? I mean, I think that list is sufficient. Maybe you think the fact that it goes through 1, 1, and 1, -1 is interesting, but label those if you want to. Okay, cool. There's the graph of x squared. I want that function. Which of the moves in that thing should I deal with first? The negative in front. So let's get negative x squared. And you don't need the parentheses I just drew, but I really want to emphasize the negative is not inside of the parentheses. All right. What does that do to the graph? Flips it over the x-axis. And in fact, I think you could recover this fact out of the fact with c. We're going to multiply all the y values by -1. So to do that, we reflect over x-axis. That point is here. All right, what should we do next? Yeah.
Either the -2 or the +3.
either the -2 or the +3. I'm just gonna do them both at the same time. So the -2 will make us go right 2. The +3 will bring the thing up 3. So this point at 0, 0 will go right 2, up 3. And it'll still generally carve down. Let's see. Even though this is an intermediate step and it's not like the final graph, I'm gonna like at least make sure I have the right y-intercept. So you get the y-intercept by plugging in x equals 0. So let's plug in x equals 0 to negative x minus 2. Then you square it, then you add 3. Plug in x equals 0, you can do it in your head, do it in your head, write some stuff to the side if you need to. Okay, that's the I think I get -1 when you plug in x equals 0. Cool. 0, -1. And we could also like be really careful and find the x-intercepts, but like, especially since it doesn't ask for it, x-intercepts just take a little bit more algebraic walk to find, like you have to solve an equation instead of just plug something in. I don't want to. All right, what's the last thing we need to do? Well, maybe, what's the last ingredient we need to deal with?
The 1/2.
The 1/2 on here, so let's write that. -1/2 x minus 2 squared plus 3. And I think I'm going to describe this step a few ways. So on the one hand, just based on what we wrote on the previous page, we need to divide all x values by 1/2. Divide all x values by 1/2. And just because that's a weird thing to say, I'm also going to write it symbolically just to make sense of what it means. So all the new x values will be the old x values divided by 1/2. All right, so what that really means is all x values double. So I don't know, like, maybe I belabor a point that people wouldn't struggle with, but like, when you write it out and there's like a division, but you're dividing by something that's already divided, like, be careful. All right, so I need to double all the x values. So I guess right now I have these 2 points labeled. Let's just track those 2 points. Where does the point 2, 3 wind up?
4-3.
4, 3.
Isn't that called like a horizontal stretch?
I call that a horizontal stretch. And I guess that I'm going to flip over to the next page to address that bit of, to the previous page to address that bit of language. I'm going to add that to the definition. This point at 0, -1, where does it go?
It stays there.
Stays put. And it's still parabola-y looking, but it needs to be stretched out. So I wind up with that graph. And indeed, does that look like we've just like taken this whole thing and stretched it away from the y-axis? Yeah. So I'm going to build that language into the comment on the previous page. So if you know the graph of y equals f of x, then when you get the graph of c times f of x, you stretch vertically by a factor of c,
when you multiply the x inside of the parentheses by a number c, you compress horizontally by a factor of c. And maybe I'll add one more quick thing. If c is less than 1, then stretch. How do you spell stretch?
STRETCH.
STRETCH.
Happily, I'm not going to judge very harshly by spelling, as long as I can make sense of what one you're trying to say. And I don't know, like, I'm a native Canadian, so you'll notice that I drop a few more U's in my words than is maybe standard in this country. So if C is less than 0, then stretch means compress, and conversely. So we did in the previous one is we compressed by a factor of 1/2, which meant we stretched by a factor of 2. That seems sensible? People feel pretty good? Think you'd do an example on your own? Nice. Then, before I do that, let's do a quick multiple choice. So we just did all that walk. So let's suppose that I then gave you this multiple choice question. Which of these 3 graphs might be the graph of the function that we literally just graphed? So stare at it for a second. See if you can make sense. Well, let's see. How many people like A? Alright, see if your head's right. How many people like B? Anyone like C? Cool. Anyone have no ideas how to proceed? Alright. So, folks who said A, why A? Like, what was the deciding factor? Yeah.
The vertex is at 4, 3.
Yeah, so here's one thing. We just found this turning point. It's at 4, 3. 1, 2, 3, 4. 1, 2, 3. Yeah, I believe that point is at 4, 3. And let's just check the other ones. That turning point, does that appear to be at x equals 4, y equals 3? Does that turning point appear to be at x equals 4, y equals 3? Cool. So if you can actually, if you just solve the problem directly, then it's easy to recognize multiple choice answers from a graph. Anyone make their decision a different way? Yeah.
I plugged it in, well, basically I plugged in values that I saw kind of quickly, so, I looked at all 3 and I was like, okay, if I plug in, 4 from A, then I get, 0 plus 3, so it worked.
Nice.
And I made sure that the -1 was also correct by, x equals 0.
So that looks like when x equals 4, y equals 3, plug x equals 4 into that, it looks like you get y equals 3. And you also plugged in 0?
Yeah.
Nice. 0 should go to -1. Check if you plug 0 in, you get -1. And then I guess you also need to do those same checks for these ones. Because plugging in some points means that this doesn't seem to be the wrong answer by those 2, But now you need to disqualify the other one, so for safety's sake, you should probably also plug in x equals 1, make sure you don't get 3. You don't. And maybe plug in x equals 2 and show you don't get 3. I think that would do it. Yeah. Any other strategies people used? Yeah, I think those are the two reasonable ones. I guess a thing you could try to do is you could say, well, that 1/2 should mean it gets stretched horizontally. Because it's getting compressed by a factor of 1/2, so it's getting stretched. That looks like it's horizontally compressed, so better not be that one. I guess that looks like it might be being stretched, it's hard to tell. So get it down to A and B by just using that vague idea. Cool, people feel pretty good? Nice. So the next thing in this set of notes is combining these ideas with the ideas of piecewise functions. Maybe before we just do that, do people think they would benefit from another example of the type that we just did? People want to do another one of those? Oh, okay, cool. Let's talk about piecewise functions. So there's not going to be any new ideas here. This is just going to be synthesized 2 old ideas. So let's suppose I asked you to graph this function, x minus 1 if x is less than 2. X minus 1 squared if x is between 2 and 3 with endpoints included and excluded as labeled. And x is equal to 3 when 3 is less than or equal to x. So the general strategy with graphing piecewise functions was graph each piece and then highlight where we care about each piece. While being careful about endpoints. So let's graph each piece. Y equals x minus 1, is that easy to graph? Tell me about the graph.
It's a straight line.
Straight line, slope is?
Slope is 1.
Slope is 1, y-intercept is?
-1.
-1. And that's enough just to say everything, right? Alright. And the slope is 1, so I guess it goes up. Does this. Alright. And the other thing I'll do, you don't have to necessarily do that in this step, but I will. Let's highlight where we care about that graph. So for what x values do I care about that graph for this piecewise function?
Anything less than 2.
Anything less than 2. So I guess
To excluding, or yeah, excluding 2.
excluding 2. Okay, cool. Happily, my pens have erasers. So that's the piece of this graph that I care about, and let's even emphasize where that point is. So it's at x equals 2, and what is the corresponding y value?
Uh,
1? How'd you get 1?
I don't know, I just guess.
Oh, all right. Yeah, the slope is 1, so if you start at -1, 0, -1, you go over 2, you'll go up 2, that'll get you to 1.
Yeah.
Alternately, just plug in x equals 2, right? 2 minus 1 is 1. All right, so let's start with that. I'm going to put that over here. So here's this point at 1, 2, up 1, 2, 1, and then it goes down at a slope of 1. All right, so I know that much of the graph of the resulting piecewise function. X minus 1 squared. How would you get the graph of that?
Could you move the paper a little bit? Thank you.
Parabola of over 1
A parabola that's been shifted over by 1
from 0, 0.
from 0, 0, and by over you mean right or left?
Right.
Awesome. Yeah, so that vortex of the parabola has been shifted over to 1, 0, and, oh, I don't want to do that, this should be in black. So far so good?
What x values do I care about this graph?
X values between 2 and 3, including the 2.
Between 2 and 3. So if there's 2, there's 3. Looks like I want to include 2, exclude 3, and include everything in between. People feel good? Let's label those points. One of them will be at x equals 2, comma, some y value. The other one will be at x equals 3, comma, some y value.
Tell me those y values.
2, 1, 3, 4.
Do I hear a 2, 1, and a 3, 4? Do I hear a second?
Yeah.
Awesome. Do I hear a call to like discuss? Nice.
Yeah, you plug in those x values, see what you get. 2, 1, 3, 4. So let's copy that over. So that 2, 1 is happily the exact same point as that open circle was. 3, 1, 2, 3, 4. There it is, and it's like kind of bendy, and then an open circle at the end. And it's an interesting point, so I'll label it. All right, the last ingredient. Y equals 3.
What does its graph look like?
I mean, that's like an example of a question that's so easy it's hard to answer in a way that's not just repeating the question. It's like,
It's
hold on.
just a solid diagonal horizontal.
Awesome, yeah. Horizontal line at y equals 3. Because of that, bigger than or equal to, it looks like I want to start at x equals 3. And then go to the right. So I guess that's the point 3, 3. So over here, I'll start at the point 3, 3, and go to the right. So it looks like this graph has a jump at x equals 3.
Neato. So if you have a piecewise function and you know how to graph each piece, you know how to graph the piecewise function. Graphing some of the pieces might require some of this graphing by transformation stuff. Groovy.
Ooh, and there's even like a Desmos thing right there if you want it. So I think with the next 5 minutes or so,
Well, maybe I'll see. Do people think they could repeat a similar example on their own? Anyone have concerns that they don't think they can? All right, then I will ask you.
here's another piecewise function. Follow the same algorithm.
Graph each piece, emphasize where you care about it, put the pieces together. And I'll encourage you to collaborate with those around you. If that means breaking up the graphing of the pieces, great. If that just means checking your work, that's cool too. And while you do that, I have the next chapter work and notes to hand you.
Alrighty. Shall we come together? People feel okay about this? And let's jump straight to you describing to me the graph of the results. So tell me some interesting points that are on the graph of the function.
Negative 1, 1, 0, 0, and 1, 1.
People agree those are points on the graph? Alright, so I guess that's where like behavior changes. So what does the graph do to the left of negative 1? Decreases and like vaguely parabola-y? And I guess decreases is kind of right, but right, technically that's an increasing function because as x's go left to right, it goes up. I listened to what you meant. Between negative 1 and 1, what does it do? It like does absolute value? People wind up with a graph something like that? Groovy. With my last few moments, maybe I'll just say, well, let's take a look at that. Looks like there are no discontinuities or anything, like it doesn't ever jump. It has places where it tawns sharply, but no actual discontinuities on the graph. Let's also do a quick using Desmos to piecewise function demo. So it looks like this description was when x is less than negative 1, you have negative x plus 1, square it, and then add 1. When negative 1 is less than or equal to x is less than or equal to 1, you have the absolute value of x. And then when 1 is less than x, you have negative x minus 1 squared plus 1. So, the reason I wanted to close with this is just to show you this notation for how it is that you can have Desmos graph a piecewise function. You just graph each piece one at a time. Cool, does that feel good? All right, we will start in next time talking about quadratic functions. So we're going to start the sequence through this class where we start getting hyperfixated on a single flavor of function. And then we'll build up these new and more complicated functions. Quadratics will be the next one on our list. Have a good day.